Welcome to the last talk of the day. I usually get very nervous during these talks, so on the tram ride over, I made some notes. Milk, eggs, toilet, never mind, toilet. Okay, shopping list on other side. Stand up straight. Don't be self-conscious of shiny, bald head. Don't train wreck your talk like last year's. Unfold paper for presentation notes. Have fun. Don't read these notes out loud. Oh, okay. I'm not as nervous now. I hope you aren't. So yes, the talk is about virtual FPGA boards. But first, I should mention my collaborators. I was able to work with two excellent programmers who also happen to be my nephews. And a good nephew always takes every opportunity to embarrass his nephews. So this has been quite a few years ago, enjoying some chocolate ice cream. And this is Ollie. Also, he really enjoys chocolate ice cream. They're both very talented, and they've visited me here in Prague. Here's some proof. This was a little while ago. And Ollie was the lead singer for a metal band when he was 6 years old. And I know you don't believe me, so I'm gonna prove it. When these connect. Go. Always happens during demonstrations. Okay, here's Ollie, lead singer of a metal band.
Go. Bring the ice down. Bring the ice down.
Their mother's gonna kill me. Hello, by the way. I know they're watching. Okay, back to the talk. Okay, what's a virtual FPGA board? It's when you're interfacing with an FPGA board that isn't real. Why would you want to do that? And that was sort of the genesis of the talk. I took some FPGA courses, and during the first labs, you're struggling with the whole tool chain. Pretty soon, all your time's up. And I've made very little progress. So I said, well, I can take this home, right? The board, power supply, and all that? No, you can't. It's like, what am I supposed to do? It's like, well, you could write some test benches. And it's like, that makes the problem worse because I'm already struggling with the VHDL. So Abstrakt, oh yeah, this is just one page. It's 5 meters long though, so I gotta go quick. Okay, so what are some examples of development boards? We used the Tarasic D10 and some similar boards, but there are also ones that are very capable and not that expensive. Okay, how do you program them? You do it with some sort of HDL, typically VHDL or Verilog. And for people that are used to programming, there's a little bit of a mental shift. that you need to program FPGAs. And the standard program that you first run to make your to make sure your tool chain is all working, it's called Blinky. So you hit a button, light turns on the board. But even Blinky, in this case, you can see here, it looks like a for loop. So you're thinking, oh, okay, the FPGA is executing this for loop. No, it is not. This is telling you how to construct what's in the FPGA. So this is just shorthand for what goes on the FPGA. Everything in this process happens concurrently and simultaneously. So you have to keep that in mind when you're programming FPGAs. Okay, these are some examples of proprietary tool chains, either the AMD Vivado, Intel Quartus. We used Quartus in the class I did, but there's also open source tool chains. And it goes through the same process of synthesis, verifying that it's syntactically and grammatically correct, what you've given it, either for VHDL or Verilog. And then you have to place and route it, which means given your FPGA, you've got to find out where this circuit, which is mostly a bunch of lookup tables, goes where and connect everything together. And that becomes the bit stream, which gets flashed on the FPGA. Then start clocking it, and it does what you told it to do. Okay, so if we're going to simulate it, we don't have to do a lot of that. There's no placing and routing or anything like that. And we can use some open source tools to do the simulation. Two big ones are VHDL and NVC. So that will take, for example, your VHDL and simulate it directly. You can tell the simulator how to clock it, and it will give you the outputs. So you give it the input, the simulator gives you the output, and you can do anything you want with it. Here's a summary of some of the tools. Okay, I should mention that it's not just VHDL and Verilog. There are several really good and up-and-coming tools. This is a table that lists a number of them. The point that I wanted to make sure that I said is the development going on in high-level synthesis. And in this case, you're not really dealing with the hardware hardly at all. So you would say make a C++ program, and then this high-level synthesis would take that and go all the way down to either Verilog or VHDL, and then you can go through all the normal tool chain to program the FPGA. So you could write, say, an FFT in C++ using the high-level synthesis and get something that you can load straight into your FPGA, and it'll do it. Okay, so now we're back to the problem. After failing miserably at my first lab, I had no board. In one class, I had no access to the lab or the hardware. The other one I could, but then I'd have to get on the tram, come down here, draw 2 keys. So it was a lot of overhead. So we could make a simulator. And it's on GitHub right now. Oops. Is this showing up? Yeah. Okay. And there's an extensive README that has all the prerequisites, how to download it, execute it, and we'll do that in just a minute. How to use it, etc. And the three major components, well, I guess, well, three. One, Python. Two, CocoaDB, which is the co-simulation, I've forgotten what it stands for. But it can run Python in another process, and Pygame for the display. It's usually used for simple two-dimensional games, but you can do a lot with it. The extra component that I used, which I guess is a minor contribution, Amaranth, which was on one of the tables I slid past real quick, is a all Python FPGA programming tool. Well, they made another repo that has loads of boards, 76 of them, I think. And so what I did is I stole all their work, it's open source, and took all the parameters so that now I don't have just one FPGA board I can run my VHDL on. I can pick and select any of those. And so the software that we have in the simulator has the same interface that the Python Amaranth project has, and takes all the parameters out of the Amaranth boards to generate the virtual board that it runs on. And again, this is just the beginnings of the project, so not everything in the FPGA boards is implemented right now. In fact, it's pretty much just a minimum. It knows all the specific FPGA pins, switches, momentary switches, and LEDs. There's a lot of other I/O that's on, say that. This is what we had in our class. So this is just the FPGA, and then you can see all the connectors for different I/O and displays, 7-segment displays, what's in there, loads of stuff. So I'm only implementing a very small portion of it. And there's even stuff on the back of the board. Why not use both sides? But most of it's on the front. Okay, and I had to simplify a little bit so that the simulator had something to work with. And so for the beginnings, there's like a standard interface. So you have switches, buttons, those are the momentary switches, LEDs, and then just because it's useful, there's also a clock defined with a counter going on inside. And so there are some blinky examples that I'll show you. And so here's the demo. So here, let's open up a window. Is it on up? Okay. So let's go into my temp directory, nobody home, that's good. And then let's go back over to the README where all the instructions are there. Fortunately, I've internet access, so it downloaded it. And the next step, it's in the README, is I'm using UV for the project management for Python. Just run sync. And so this is absolutely all of the dependencies. It's already loaded up. We look in the directory. It even defined a virtual environment. And so now, how do we run it? So launch. So copy that, go over to our newly installed. So UV run means UV take care of where you're getting everything from. And it did that through the sync and the Pi project. And so we run it. And so simulator is running now. We can pick a board. Let's pick the ULX 3S. It's got some LEDs and buttons and switches. So this is just the beginning, but it shows the what's defined so far. So this is like the notional FPGA board. So you have your FPGA, you have your LEDs, the buttons, which are the momentary switches, and then the switches that are, you can set it on or set it off. Okay, we already selected our board. I'll just show you this. Here are all the different VHDL files. So if we pick walking, and then you can pick your simulator. Right now it's just NVC or GHDL, and say go. So this is what you'd see on the board. And then there are some buttons that are in the VHDL file where we can change the direction or turn everything on. Here, I can make this bigger. And this is all a Pygame display. And then the switches affect where it's tapping the clock. So very simple VHDL, but this was all I was doing in the first couple labs was writing VHDL files, clicking buttons and watching LEDs. And then just to give more information and to enhance some control, I hit S, and it pops open a panel with some statistics. And you can see that our effective clock rate is only about 600 kilohertz. This board runs at 25 megahertz. So because we're simulating it on the CPU, this is considerably slower than the actual hardware. But if you just want to see functionally and point and click through your VHDL file, it works. And then this won't be particularly effective since the actual board speed's fast, but we can slow it down. So for example, if things are happening too fast, you could slow down the simulator so you could see every single output change. And then for boards that have multiple clock frequencies, which we get from Amaranth boards, you can select what the virtual clock frequency is here. And there's some status, what board, what VHDL, which simulator, and it's also storing some statistics and files so that we can try to enhance the performance. Okay, so, well, just as an example, just to prove that it works, let's load another board. Let's see. So this one has the same number of LEDs, different number of buttons and switches, same program, go. So this is using a different FPGA and define different I/O, but using the same VHDL program. And you can do that for all of these boards. And whenever Amaranth boards adds a new one, we get it automatically. We just derive all the information from them. Okay. So that's a quick demo. Okay, current limitations, you've already seen a lot of them. Okay, I want to jump ahead to this part. I have 4.5 minutes. This was also an experiment for me. I'd never used agentic AI before. I'd used regular AI to like paste in the code and say, I want it to do this extra thing. And sometimes it came out correctly, sometimes it didn't. My nephew, who would have been here today, but he's doing big international business in Japan right now, who works for a very large corporation. They have access to extended context length frontier models and their LLMs. And he showed me how he uses, in his case, Claude Opus. And that's, for me, expensive, but I could afford Claude Sonnet. So we worked together using Opus, and then I continued the development doing Sonnet. So I took it on as a challenge. How much actually writing code can I not do? And I can tell you that I never edited a code file directly, and I never used an IDE for any of this code. And you might say, oh my God, how can you do that? He showed me how to use it and to go in small bite-sized chunks and having it write tests the whole time. And it was actually amazing how well it can write tests. It would come up with corner cases that I probably would never think of, and then write a test for it. And so it was an iterative process where we started small. One blocker was, can we actually get the information we need from Amaranth boards? So we started there. Can we create the display that we want to see with Pygame? And then we did that. Can we put them together? And the whole time, Claude was keeping the whole project, Python, CocoaDB, Pygame, Amaranth boards in context, so that if you were asking for something new or a change, it was taking into account how that might affect something else. There are potential problems. I'm glad that he showed me how to use it better than I would have. And that's by doing it in small chunks. There are possible problems. For example, this is BirdBuddy, which uses AI inference to just take photos of birds. And that's me with just a kid's toy. So it decided that either that was a real bird or I was maybe a squirrel. It doesn't tell you. So you have to be aware of the consequences and review the code. Now, just because I didn't edit it directly or use an IDE doesn't mean I didn't look at the code. So I did review all the changes, and Claude is good about telling you exactly what it wants to change. You can ask it to plan. I want you to add this feature and present options and recommendations to me. And it'll do that. And it'll show you where in the code, which files will change, and you can decide the direction that it goes. And it's really powerful. And for me personally, could I have written the simulator? Yes, but it would have taken me much, much, much longer. And so this was 3 of us working. Once a week together a lot, and then me just occasionally over the past month or so. And we were able to produce that. If it was just me doing it, it would have taken months, literally. So the bottom line is, and I'll post this, it's an ASCII doc. I'll post this on the conference underneath my talk, but without any hardware, you can take your VHDL file, run it, click some buttons, throw some switches, and watch the output on the LEDs. Thanks.
Questions? So what is the limit? Would you use it for like 6502 simulation? Simple 8-bit CPU or simple that or?
Okay, yes. That was in the limitations. And so I'm clocking the FPGA. At first it was all through Python, where, clock signal goes high. Okay, now clock signal goes low. And GHDL or NVC would do whatever it's supposed to when the FPGA clocks. That was really slow. So what I did with Claude is I moved the clock in chunks inside the simulator. So Python tells GHDL how many times it should clock before it tells me it's done that, and then look at the output. So for a processor, this would be really, really slow. So like if we did like a RISC-V in this way, it wouldn't work. Now, depending on what you wanted to do, like let's say you wanted to use the simulator to run Linux on RISC-V or something, then doing it this way, no, you can't do that. But maybe you could use something like QEMU or whatever to take over the process, and you could interface it all that way. So this was meant because my first few labs in learning to program FPGAs was a rough experience. So I wanted to write simple VHDL, throw some switches, and watch the LEDs.
Okay, thank you very much.
Yeah.